says 24.
Oh.
Yeah.
I could probably do that.
You should do that.
Good idea.
Yeah. Always a good idea.
We'll have an exciting afternoon.
Yeah.
Symbolic math was pretty interesting.
Symbolic
like,
math?
You know, like the very simple algebra system.
Yeah.
I mean, it wasn't really symbolic, but you could.
The constraint solver, you mean? Or
Yeah.
Yeah. That's John's homework problem from constraint programming. Yeah.
Well, no, it's not mine. I stole it from.
Oh, you stole it from? Okay.
Original structured interpretation of computer programs.
Ah.
Book.
Oh, that is true. They had
constraint
that.
programming in it.
Yeah.
I guess I did add the squarer.
Okay.
Oh, sorry about that. If you're still working on the homework, that's okay. Don't panic if you don't get it in. But please let us know if you need more time.
Yeah.
So that we can give you explicit extensions. And I know there's a lot of other stuff going on. Yeah, if you have like so much work that you can't do it today, that's okay. And also, we do give credit for sincere effort,
Yeah.
even if you don't figure out exactly how to solve all the problems.
Yeah.
Okay. And I think we will have a third homework.
Yeah, I don't know on what yet though.
But I think probably one question will be on concurrency.
Concurrency, yeah.
So pay attention.
Okay. Welcome to, what is it, lecture 8 now? CS98-52. Today's lecture is going to be about how to add, I guess, or that's the first part of it, on concurrency and parallelism, and how there's a lot to be said about parallelism. I'm just going to cover a few points. And I'm going to start off by talking about how to add. So you all know how to add, I think. Exciting. We're going to go over it. We're going to work in binary first. So the idea here is you have two numbers that are each n bits. So n equals 8 is like 1 byte, right? And you want to add them up. So how do you add them? First number, let's say it's like 1, 0, 1, 1, 0, 1, 1, 1. And the second one is 1, 0, 0, 1, 1, 1, 0, 1. And if you add them, 1 plus 1 is 0, right? You carry the 1. 1 plus 1 is 0, you carry the 1. 1 plus 1 plus 1 is 1, you carry the 1. That's 3 in binary. 3 is 1, 1. Okay? Any questions on the binary so far, or any of this? Does this make sense? Okay. So the first question, or the first thing is, this is called ripple carry add, where we add 1 and then pass the carry, and then we add and then pass the carry. There's a couple questions. First question is, how big can the sum be at most? Yeah.
N plus 1.
Yeah, it could be n plus 1 bits, right? In the worst case, right? And how long does the summation take in the worst case? Someone else? Yeah.
I think it's always a linear. It's linear in the length of the integers.
Right. So if this is n bits, then it's going to take theta of n, right? So this is a theta of n operation. And why? Because we're going through bit by bit, and each one depends on the previous one, right? So there's no way you can compute this one before computing this one, because you need to know whether there was a carry. Or so I claim. Turns out there is another way to do it. We'll get back to it later. But this is our motivation kind of for this lecture of parallelism. Okay? Questions so far? No? OK. So a little bit of history on computers and parallel programming in general. So you might not have heard of this, but there was a guy named Charles Babbage who lived in 1791 through 1871. And he invented a couple of machines, or he didn't physically create them, but he designed them. They were called the difference engine and then the analytical engine. And those are said to be the first computers that were ever designed by humans. Okay? If you think about it, this is a long time ago. The first actual computers were created back in maybe 40s. But he created what's called like an ALU in a computer, which is designed for arithmetic. He designed a lot of things. But the first computer that was oh, sorry. And the first description of what's called MIMD, I'll get back to that, parallelism was also in 1842. So this guy was thinking about parallelism way before there were any computers. Okay. But MIMD stands for multiple instruction, multiple data. What it means is if you want to perform a lot of operations on a lot of things, they call that MIMD. Because there's different things you could do. You could do one operation on a lot of things. You could do a lot of operations on one thing. And you could do a lot of operations on a lot of things. These are all different types of parallelism that you could have. The first description of that kind of parallelism was by also Charles Babbage back in 1842. But the first theory of computation in general was by Alan Turing, after whom the award is named, which there's going to be a lecture, or a Turing Award lecture after this talk. So if you want to stay, you can stay for that. Room's going to get packed, by the way. And anyway, so he was the father of like computing and computing theory in general. The first analog computer, which is a thing, we see digital computers, but there were analog computers. They were created for World War II back in the 1940s. And the first digital computers were also created back in the 1940s. That was called the ENIAC, was the first one. It's also used for math here. And the first description of parallel programs was made in 1958. I don't know too much about the history of these, but the first multiprocessor system was created in 1969. And then there was a lot of research in parallel computing actually in the 1970s. Now, this was at least surprising to me when I started learning about parallel computing because it wasn't a hot thing like maybe in 2000s because computers were getting so much faster that there wasn't a lot of focus on how to parallelize. They just waited for the next chip to come out and it would be like faster. So there wasn't a need to use parallel computing. But there was a lot of research back in the day. Then it kind of faded away. But then it gained a lot of traction around 2001. Because once CPUs started hitting their speed limits, then people started looking at parallel computing again. So that's kind of what prompted also the creation of the Aspire Lab and or I think a lot of things. There was a lot of work on parallel computing. So long story short here is that parallel computing has a long history. It's longer than I initially expected, and there's a lot of useful research from the last century that is still applicable. So it's useful to know about them or go back if you want to read about them at some point. Okay, so some general terminology in parallel programming that you should know about. First thing is called a process. You may have already heard of this term. If you use like Windows, you bring up Task Manager, you see a bunch of processes running. Those are like programs that are running on your computer. Okay. Processes are by default isolated from each other, so they can't affect each other. And that's as a security mechanism. It's for convenience. It's for everything. But you can have processes running in parallel, and they're independent of each other by default. Okay. There's a notion of a thread, which is it's hard to explain, but it's like a unit of program flow. So it's kind of like you could think of it as a process, but it shares all the memory it has with all the other threads in the same process. So when you see a process in Task Manager, and you see, let's say it's using, I don't know, 100% of your 8 CPUs, that probably has 8 threads running in that one process, each one using a separate CPU. And threads each maintain their own context. So context here means where in the code the thread currently is and what its local variables are, what the parent frame is and things that you've learned. Those are all properties of threads. Okay? But they share the same memory as a process. Now, thread context, I just explained, it includes all the information that the thread needs in order to run code. So it includes the location of the code that it's currently executing, which keeps increasing or jumping somewhere else, as well as the current frame in which it's at, and all the local variables. OK? Questions on this so far? What these mean? Yeah.
So sorry, is the memory part of like the local variable?
Mm-hmm.
Like are global variables separate from the thread context?
Yeah. So globals are shared for all threads in a given process. Local variables are isolated. They belong to the thread. Yeah. Any other questions? Or at least as a first approximation. It's possible to sometimes share local variables depending on what you're doing, but for now we'll just assume they're separate. Okay. There's a couple of more terms you should know. They're concurrency and parallelism. They're sometimes used interchangeably. They don't mean the same thing. Concurrency means you have overlapping operations. So you have two operations where one begins before the other one ends. So let's say you send a network request, and then you send another request, then the first reply comes, then the second reply comes. These are concurrent requests because the first one goes on before or the second one starts before the first one finishes. But they're not necessarily happening in parallel because you might be only doing one thing at a time. You might not be doing two things at a time. Anybody confused about what I just said? No? Yeah.
Well, can you explain again what exactly the difference is between those two terms?
Yeah. So concurrency means that, so you have operations that begin and end at separate times, but one of them begins before the other one ends. Okay? But you might still be only doing one piece of work at a given point in time. You might be doing like a little bit of this, a little bit of that, and then a little bit of this again, a little bit of that until they're both finished. Okay? That's still concurrent, but it's not parallel. Parallel means actually running at the same time. And to run things in parallel, you actually need multiple processors to run them. Yeah?
For simultaneously occurring operations, do you mean operations within a process or multiple processes?
It's just a general term. It could apply to either. But we're going to be talking about actually both. So yeah. Other questions? Okay. Sometimes they're used interchangeably. They don't mean exactly the same thing. But so this means parallel operations are always concurrent because they happen at the same time. So one is happening before the other one ends. But it's not the other way around, right? Parallelism does give you a speed boost because you do multiple things at once, so your tasks finish faster. But concurrency doesn't do that. All it does is it lets you start something before you finish something else, which is also useful because if you're like starting a program on your computer, you don't want to have to close all the other programs, right? You want to be able to multitask. That's concurrency, okay? But you can have concurrency on one processor. You don't need multiple processors. Questions so far? No? Okay. Now there's a term distributed computing, which means running programs on multiple actual computers, not just multiple processors on the same computer. It's a more difficult thing to implement because first thing that comes up is fault tolerance. The more machines you have, the more likely it is one of them is going to fail, either for hardware reasons or software crashes or anything. And that's a topic that comes up a lot in distributed computing. Whereas when you're running, yeah, or do you have, oh, no question. And whereas when you're running on a single, oh, do you have a question? Yeah.
Oh, yeah.
Yeah.
Is this related at all to how some, I guess, projects,
How what?
how some projects, like the giant internet we've seen Prime Search, they ask for volunteers to run the software on their own computers. Is it related to that?
Well, I mean, they are parallelizing the work there. So if that's what you mean, yeah. They are distributing the work, and they probably have some fault tolerance because you'll shut down your laptop. You don't want to break what they're doing. So they'll have to code things that are robust to problems on computers. But that's one notion that comes up. And there's another one, which is lack of shared memory. When you're running on one computer, you can share memory and use the same variables everywhere. When you're running on multiple computers, that's not the case. There's also more limited communication bandwidth. Networks are slower than just reading and writing from memory. So concerns come up. Time also becomes problematic. A global notion of time doesn't necessarily exist, depending on how you design your system. So there are a lot of problems basically that come up in distributed computing, and it's a whole field in itself. I'm not going to be talking too much about it, although I will a little bit at the end. But it's something to keep in mind. It's more complicated than just parallel computing. There's a lot of rich literature on parallel computing and distributed computing in general. There are models for computation that try to guarantee things like a certain amount of throughput, a certain amount of latency, things like that. I'm not going to be covering these, but there are, you can look these up if you're interested. Okay. So enough of concepts. Let's go. Oh yeah, questions.
So when we're talking about distributed computing,
Mhm.
is there like some sort of a hard upper bound that says, okay, if you have more than this many computers,
Yeah.
it's not as efficient? Just is there something?
Yeah, there's something called Amdahl's law, and it says that if you have a task that's like only p% parallelizable and the rest of it is sequential, then you can parallelize all of this, but it won't get any faster than the other one. The math is pretty simple, but it can, if you don't pay attention to it, it can trip you up. You can think you can get an infinite parallelism. It's covered in 61C. So yeah. Other questions? Also, depending on the algorithm, there are algorithms that can't be parallelized. Okay, so that's also another issue. Okay, so here's an example of what multi-threading looks like in Python. It's the simplest example I could think of. So there's a module you can import called threading, and you can say create a new thread. The function you're running, let's call it print, or let's use the print function, and we're going to pass it a. Okay. So what this does is, as soon as you say t.start, it's going to start running the print function in a separate thread, independently from your current one. Okay. When you say print b, it's going to print b in the current thread, which is the main one. There's always one thread at least in a process. And then you're going to say wait for this thread to finish running. So that means you started another thread. It's going to print a, then you printed b. There is no ordering here between whether a gets printed first or b gets printed first. Anybody lost on that point or no? Get some blank faces. Yeah.
What exactly does t.start and t.join do?
Yeah. So t.start means start running this function with this argument separately from the current function. So that currently you're running this piece of code. It says just start running this piece of code independently from me. T.join means wait for that piece of code to finish running and then continue. Yeah.
So does it have like a new global frame and stuff on the other thread?
It doesn't have a new global frame, but it has its own like function frame, like call frame. Yeah. Okay. Yeah. Yeah.
So like if you define variables after t.start and you're using those in the thread, would they work sometimes and not other times?
After t.start, yeah. So it just depends on the order in which things happen. Right. Exactly. Yeah.
But wouldn't it just end up like printing a as soon as you hit enter?
Wouldn't it what?
Wouldn't it just end up like printing a as soon as you hit enter?
So no. So wait. Where do you press enter? There's no enter here.
Oh, they're running this fast separately.
The thing is, if you say start, all it says is it starts running this. But it may end up that you do this before it actually ends up doing the printing. There's no guarantee on the order in which things happen.
But if it started that one first,
Uh-huh.
wouldn't it end up finishing that one first because they're both print?
Not necessarily, because the way a computer works, even on a single processor, is it does a little bit of work for one thread, then it does a little bit of one for the other thread, then it does a little bit for a different thread. So depending on how far it gets, and there's a lot of work to do for printing. I mean, it looks just like print in Python, but it's really complicated. Then depending on the order in which things happen, it could be in a different order. Yeah.
If I have a 2-core CPU, then is it guaranteed that one of the threads will be executed on one core and then the other?
Nope. There's no guarantee. I mean, you can guarantee it using specific functions that the operating system gives you sometimes, but by default, there's no guarantee. It could just do them on the same CPU, just time slice them is the term, or it could do them on different CPUs. Okay. So the one thing to notice here is that printing happens to the same screen. So there has to be some coordination at some level. You can't just print to the same place at the same time because you want them to appear one after the other. So there is some coordination happening underneath, but it's as far as we're concerned, these are happening in parallel, and there's no guarantee on which order they happen in. We just know they won't happen at exactly the same time. Any other questions on this? No? Yeah.
Is a thread like is a thread, does the word refer to necessarily like two different things, like a parallel process, or can you just have two concurrent things running on the same CPU?
It could be on the it could be on the same CPU. They're called threads if they have separate frames and they're executing independently of each other unless they explicitly coordinate. Yeah. Okay. So what we say is there's something called a race condition, which you should know about, which is If a thread attempts to access something that's being modified by a different thread, that's called a race condition. Because they're both racing to use the same thing, one of them is trying to modify it, so there's no guarantee on which order things happen in. Okay, one might see things after the changes, one might see things before the changes. Okay? Generally, they're bad. There are occasional exceptions, but in general, you don't want race conditions in your program. Okay? Here's a very simple example. If you import threading and you have a shared global variable called LST, and in your function you just try to increment the first element, what happens is if you start another thread to do exactly the same thing, and then you do that too, this could end up being either 1 or 2, depending on the order in which things happen. Now, why is that? Because this, in order to increment this, first you need to read from it, and then you need to write to it. So both threads might read the value and it's 0. They might both add 1, and then get that the new value should be 1. And then they write to it and they both end up putting 1 into the same slot. Okay? Or they could happen in sequentially where one writes and then the other one reads and everything is fine. Okay? Questions on this? No? Okay. Now, you don't want these, so how do you prevent these? There's something called a mutex. It's short for mutual exclusion. In Python, it's called a lock. Sometimes it's called a critical section. There's different words for the same thing. And what they do is they're objects that let you prevent concurrent accesses to the same thing. The way this works is the exact same code, except what I do is I create an object called a lock object. And I say acquire the lock, then increment, then release the lock. Okay? Now what this means is as soon as 2 threads try to acquire the lock only lets one of them obtain the lock, and it makes the other one wait until the other one releases the lock. Okay? So this means now this will happen sequentially, and you're guaranteed to get 2. Yeah?
Can you explain how specifically you could have 2 different cases in the first example?
Yeah. So here, so this is like saying LSC of 0 is equal to LSC of 0 plus 1. Right? So when you say LSC of 0, it has to read the value, which it says, OK, it's 0. Then it has to write the new value, which is 1. Now, if they both read the same value, which is 0, and then they both write 1, then you'll never get 2. Whereas if one of them reads and then writes, and then the other one reads and then writes, you'll get 2, because you get 0 to 1 and then 1 to 2. Is that confusing? Or?
How exactly can they read at the same time?
They could if there are multiple processors, but even if it's one processor, the first one could read, and then the second one could read, and then the first one could write, and then the second one could write. There's nothing preventing that because they're separate threads.
Then how would it happen that how could it happen that list of 0 ends up only being 1 instead of 2?
Because if the first one reads and it says the value is 0, and then the second one reads, it also sees the value 0, then they both add 1 to what they read, which is 0. So they get 1. And then they both write 1 as the new value to that slot. Okay? Yeah. Other questions? No? OK. So this is a way to prevent concurrent access to the same object, and locks are used a lot. They can get tricky. I'm not going to go into that. You'll see these in 162. But that's the idea. Now, it turns out in Python, or at least in CPython, which is what most of you are probably using, you can't actually have things happening in parallel. You can have concurrent things happening, but you can't have 2 things happening at the same time because Python has something called the global interpreter lock, which makes it so that it only executes one part of the program at a time in a given process, even if you have multiple threads running. So if you really want parallelism in Python, what you have to do is write another copy of your program and then try to communicate with it. OK? I'll show an example of that. But as far as we're concerned, I'm going to treat it as if multiple threads can actually run simultaneously in one process. It's not that different if they can't, but yeah. There are other flavors of Python, though, that actually can run in parallel. There's Jython, there's IronPython, and those can actually run Python code in parallel. So It's not a Python limitation. It's just the limitation of this particular version of Python. Okay. And one more thing on concurrency is that processes and threads need to communicate with each other, because if they don't communicate, then how are you going to combine the results and get an answer at the end? So one way is with shared memory. They can modify the same objects. Like one modifies one object, and then the other one sees the change, so it's going to do something else, and then that one's going to see the change. It's generally not preferred, but it's faster, so you might need to do this for performance. It reduces needing to copy data because you just share the same location in memory. But this means in order to actually make this happen, you can't both just write to the same thing at the same time, because then you won't know which order things happen in. So you're going to need to use locks and wait. So that can actually slow things down. So depending on what the trade-offs are in your particular program, you might find it's faster or slower. Another one, which is generally more preferred and easier to reason about, is called message passing. And I'll show an example of that. But what this does is it creates something called a queue, which is kind of like a list where you put items on one end and then read them off the other. And these are internally what's called synchronized, so that it's fine to access them from multiple threads. And they just pass data between threads. Okay? So these can happen. They don't need you to lock. But they increase the need to copy data, especially if you're passing data to a different process. There's also pipes, which I'm not going to go over. They're kind of like synchronous versions of these. But to show you actual code of what this might look like, there's a module called multiprocessing, from which you can import a process and a queue. You define a function, let's say f, that is your worker. This is an example of message passing. Okay? So you can define a function that's going to be running in a different copy of your program. You pass it two queues, the queues for the inputs and the queues for the outputs. And you say, while there is something in the queue, so while the next item in the queue is not none, you say, compute the resulting value. So let's say we want to square a number. And we put that into the output queue. Now, you could do any kind of work you want here. This is just an example, right? But if you want to parallelize your work, you would have this function running in multiple copies of your program. And to actually make it run is you say, if you're the main program, create the two queues. One is the input, one is the output. Create a bunch of processes. So let's say 4 of them, if you want to run things with a parallelism of 4. So 4 copies of your program running at once. You start all the processes. They try to read from your queue. And then they wait until there's something in the queue. And then let's say you go up to 10, and you say, put the value 10 into the queue. Or value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 0 through 9, rather, into the queue. And then you ask it, OK, now you wait for the output queue to have the response from each of these threads. And then let's say you print them, for example. After you're done, you can say, put a none value to indicate that there's no more work to be done, so that the queues can finish running. They will break out of the while loop. Or the threads will finish running. They'll break out of the while loop. And then you'll just wait for them to finish. This was a lot of code. Anybody, did I lose anyone? Yeah.
How come after we start the processes, before adding stuff into the array, they don't all just like break out of the loop and like stop?
Say that again? Sorry. When you start processes,
so in this code you start the process, and then after that you put everything in queue.
Yeah.
How come this doesn't immediately trigger the like if x equals none?
Because when you say queue.get, it actually waits for something to be in the queue. Initially the queue is empty. So it just waits for something to come in the queue, and then if it happens to be none, then you stop.
Got it.
If there's something else, then you keep going. Did I lose any of you? I'm sure I did, but let me know if you're confused. No? Yeah.
Where do you take things out of the queue?
Over here. So when you say queue.get, it gets the next value from the queue.
Okay, and that takes it out.
Yeah, and that takes it out, and you do some work in it, so like square it. And then you put it back into the output queue here.
And is this like locked so that?
So this one is internally the queues are locked. That's the nice thing about it. So you don't have to worry about locking with message passing. Internally the queues are locked, and they'll handle concurrent modifications to the queue. Yeah.
What's the purpose? Like, isn't this basically just squaring every element of this?
Yeah. So you wouldn't actually just do this for the purpose of squaring. This is just an example, but you could do more complicated work here. The point is, if you want to parallelize some work, you can do it like this. Just put whatever you want in here.
But so if there's whatever automatic locking, then wouldn't it just end up taking the same amount of time?
So right, good question. So the automatic locking happens in the put operation, but the squaring itself is not locked. So they could independently, they could independently do the squaring, and then they will have to synchronize to put things in the queue, right? So so you don't want to do this if it's a cheap operation like squaring, because then you won't get much parallelism. But if they're doing a lot of difficult work, they're doing a lot of work, then that part will be parallelized, and then the queue will be sequential. Yeah.
So the output queue, do you know what order the stuff comes in?
Nope, there's no order known. Yeah. You will have to somehow force an order if you need that. Yeah.
Okay.
Yeah. Okay. Same question. Yeah.
So are processes more? It seems like they're like threads because
they're like threads. The difference is, they're like threads. The difference is, I don't think you could just access, okay, Python tries to make it so you can actually access some of the global variables here too. But the first thing is when you actually give it a value, it's going to actually have to copy this to the other process. Now for an integer, it's going to be cheap. It doesn't matter. For a big object, like a large list or whatever, it's going to take a while. So there are implications in the performance of threads versus processes. Yeah. Oh, sorry.
So it's not like you're forking the same process. This
No.
10 things are happening, not 10 times 440, right?
No. There are 10 tasks to be done. They're spread across 4 processes.
Yes.
Yeah.
But each process continues. So the processes share the same memory. It's not like you fork this program.
No, they don't share the same memory actually. They are separate. They get forked actually. Python tries to make it best so that it's copying the program and making 4 copies.
Then
Yeah.
the queue should be copied as well.
The queue is shared internally. Python does a lot of magic to make that happen.
Okay.
Yeah.
So it's not like queue, like multiprocessing.queue
Yeah.
is different from queue.queue.
Yeah, I think I don't know. They might end up being the same implementation of queue. I don't know, but internally there's a lot of magic happening. You don't need to worry about. Yeah.
To get the values in the output queue, would you just use the same?
Yeah. Here. So we just say the output queue. The second queue is the output queue dot get. Yeah. Okay. Cool. Okay. So let's go back to the initial problem I gave you. How do you add numbers? So this is the algorithms now. We're finished with the concurrency, with the coding, but with the algorithms. So there's a common technique. You'll learn about these in 170, but it's called divide and conquer. And this is used for both sequential algorithms and also for parallel algorithms. Okay? The idea is you divide problems into subproblems. You solve the subproblems in parallel. And then you merge the results into the main result. Now this is easy to do for things like AND, OR, and XOR, if you've seen them before. AND means 1 and 1 is 1. 0 and 1 is 0, 1 and 0 is 0, 0 and 0 is 0. But the idea is if you want to do these operations, it's really simple. You just have n bits. You just spread them across n different threads. They do the ands, and then you put back the results together. You can do that with XOR 2. You can do that with OR 2. But you can't do something similar with addition, or it doesn't seem like you can. Why? Yeah.
What is XOR?
XOR just means if you have so 0, if you have 0 XOR 0, then this is set to be 0. 1 XOR 0 equals 1. It's just a function that's defined to be this way. And then this is equal to 1. And then 1 XOR 1 equals 0. It's like addition without carrying, basically.
Okay, so if you did that, you don't have to worry about carrying. You could just do the XOR of numbers digit by digit.
You could XOR them, but then you do have to worry about the carrying, right? So do you have a question? No? So the thing is, the reason it's not so easy to do something similar with addition is that if there is a carry, then your answer is not the XOR anymore. It's something else. You need to add one more. Okay? But it turns out you can do something like this, and that's what I'm going to go over. So if you have 2 n-bit numbers to add, you could try to take a similar approach. You could actually say, split the numbers into p pieces. You could say they're n-to-n pieces if you want. Add the pieces independently from each other, and then put back the bits together. Okay? well, we didn't solve the problem, right? What's wrong is what I just said, which is that you need to worry about carries. Okay? How long does it take? It's theta of n time, which I showed you in the beginning. But can we do better? So the key idea here is that a carry can be either only 0 or 1, right? So if you're adding two numbers, the most you can carry is 1, and it could also be 0. And you can add different pieces in parallel. And you can also select the correct answer based on what the carry was. So what you could actually do is split the number in half. Let's say you have a number like 0, 1, 1, 0, and you want to add it to 1, 1, 0, 1. Okay. You could actually break this into two parts and then figure out, OK, well, this is independently 1, 1. This one, depending on whether there was a carry or not, this could either end up being 1, 0, 1, or it could end up being 0, 1. You can solve these two in parallel without actually knowing whether there was a carry. You're doing more work, but if you can do things in parallel, you don't have to wait to see what the carry was. Yeah?
Shouldn't 0, 1 plus 1, 1 be 1?
Did I mess up? 1. If there was a carry, then you get a 1. Then you get a 0, and then you get this. Sorry, I can't. Sorry, my bad. 1, 0. Yeah, I can't add. Remember, I can't add. That's the same problem as other lecture. There we go. OK? So the idea here is you can actually add these independently for both cases, just without waiting to see what the carry was. And then once you do find the carry, just select the correct one. Anybody confused on this, or does this make sense? Yeah?
Why can't you just, it's only one addition. You just say, you have the like, oh, I guess you would have to do it all over again if you found out there was a carry. Okay.
Yeah, so if there, yeah. Yeah.
We still have to propagate the carry bit.
You do, but you could start these in parallel, and then you only figure out which one you pick when they're both done. So the thing is, you don't have to wait to start this one before the other one's finished.
Isn't that just more work, though?
It is more work, yeah. So with parallelism, there's a trade-off here. You're doing more work, but it helps you get things done faster, which is a little bit counterintuitive, but because you can do things in parallel, it's possible. Yeah?
So if you're splitting up the addition into 5 sub-additions,
Uh-huh.
and you have the addition all the way on the very left.
So I split this up into two parts. I said do this part in parallel and this part in parallel. You could split it up in more. You can say like 4 or 5 pieces. Yeah, so you could actually do this recursively. And that's the other thing I was going to say here. The idea is, now if I need to add, like if I said I split this up into 2 pieces, now to add this side, I could do the same exact procedure again. I could split that up into 2 pieces, figure out the left part of that independently for both cases, and then select the current one. If you do this, what you get is called a conditional sum adder. And it turns out the running time, it's theta of log n. Because you're dividing in half each time, and they happen in parallel, the number of times you can divide in half is log n. And so what happens here, what matters here now is the propagation depth, not the work that you've done, which is more work than normal. But what matters is what you need to wait for and how deep the computation has to go, how many steps the computation has to go before you get the final answer. Okay. So if you were to write how much work this is done, it's actually about n log n work instead of theta of n work. Okay. But they happen in parallel. Yeah.
Should that be a C, or?
There's a constant amount of work done at each level, and then you divide it in half and do the halves separately. So, okay. Now there are also other algorithms for this, for addition. There are a lot of them actually. Cogstone is apparently the one that's used a lot in CPUs. There are also other ones. This is apparently the fastest one, and I don't know all of them, but a log n is already optimal, at least from a theoretical standpoint. From a practical standpoint, it turns out for hardware, some of these are better suited because I was selecting all the bits based on what the carry was, that means one carry has to influence like so many other bits, and in hardware that's hard to do. If that doesn't make sense, it's fine. You'll learn about this in some other class if you do hardware. But it turns out these algorithms have different trade-offs for how many dependencies there are on the bits, and that helps for hardware. Okay. Now let's go to multiplication. So we know long multiplication. Okay. And with binary, it's pretty simple. If it's a 1, you just copy the number. If it's a 0, then you just put all zeros. Okay. The difference is now you have a lot of additions to do. It's not just 2 additions. Okay, or 2 numbers to be added. Now, one way to do this is to just group these in pairs. So do these in parallel, do these in parallel, do these in parallel, do these in parallel, and then add these in parallel, add those, and then add everything. That's going to end up being theta of log n squared time, because you have to do log n for every pair, and you have log n different pairs to add. But it turns out you could actually do it faster. So I went over this already. OK. The way you can do it faster is clever. It's called carry save addition. This is actually, I think, in 170 sometimes given as homework, sometimes not. But what you do is for every triple of numbers that you want to add, you can actually reduce that into the sum of 2 different numbers. And you can do this in parallel for all of them. What you do is you first compute all the carry bits, which can happen independently. That's just ORing them together. You compute all the sums except for the carries. That's just XOR. And now you have, for every triple of numbers, you have a pair. And for another triple, you have another pair. So you could do this recursively again. It takes log n recursion, but because the bits can be actually used to compute the carries and the sums without the carries independently, that means they can all be done in parallel in theta of 1 depth. I probably lost some of you. I don't know. Any questions on this? Yeah.
So by depth, you mean that like the physical time, not
yeah,
not the machine.
Yeah, the physical time.
Like break.
Right. Yeah.
Where do A, B, and C play into this?
So so A, B, and C are, let's say, like the numbers that you're trying to add here. So like we'll call this A, B, C. Okay. So we can reduce this into the sum of 2 numbers. The first number is 1, 1, 0, 1, 0, 1, 1, or 1, 0, 1, or 0, 1. The point is, it's additions without worrying about the carries, and the other number is just the carries. Okay? So now you can add those together later. But this helps you do all the bit additions in parallel. So you don't have to actually take log n time to do them.
Oh, so does this then work for more than 3 numbers A, B, C?
Mm-hmm.
Can you do this
Yeah, so you do this with the first 3 numbers and the next 3 numbers in parallel and the next 3 numbers in parallel. And then you get 3 numbers there, so you do it for them again in parallel with another triple. And you keep recursing to do this all in parallel. Okay? So that was, sorry. So total depth ends up being theta of log n. Let's see if I can get through the last few minutes quickly. So it turns out this is a general kind of operation, not this one, but the previous one, when we were doing addition. So we were adding a bunch of bits where each one depended on the previous ones because of the carries. Now, that's a really general kind of operation. It doesn't just happen with addition. And there's a general technique for solving this. It's called parallel prefix or parallel prefix sum or cumulative sum. There's a lot of names for it. But any binary operation that's associative, basically, you can do this with. So, or you can do the technique I'm going to describe with. So the technique is, let's say you want to compute the sum of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cumulatively. So the sum would be like 1, 3, 6, etc. So you sum up the first n numbers, and that's your new sum. You can group these into a binary tree. You can say, I'll do these in parallel, then these in parallel, these in parallel, these in parallel, and then group them into 4s. So I do these in parallel, etc. OK? Now, you can have these trees propagate up the sums from their left-hand side and pass them to their right-hand sides. So if you did 1 and 2 and it became 3, you can then pass it up and then down to this one and say, oh, by the way, the sum of everything before you was 3. Similarly here, you can say the sum of everything before you here was 11. And then you can pass those up again. And then you can say, OK, well, the sum of everything here was 10. And then you can let this one know, oh, the sum of everything here was before you was 10. So you parallelize these, but then you propagate down or up, I guess here, the sums of everything before. And if you do that, you can actually do this in log n depth again. Yes, question?
And then the branching factor is just the number of tasks you can do in parallel. So
Yeah.
We're assuming that you're doing 2, but if you
Yeah.
do 3, then
So this is assuming infinite parallelism, basically, because as many numbers you can have, you can do pairs in parallel. But in practice, you'll be limited by how many you can do in parallel. So yeah. OK. That's that. OK, last thing, a couple minutes. There's a very general pattern called MapReduce. They sometimes cover this in 61A or 61C. You've seen map before. Reduce is a generalization of addition, multiplication, and things like that, where it takes a bunch of things and it spits out one thing. Mapping just takes one thing and it spits out one thing. If your code is in this structure, you can parallelize it really easily. Okay. And the idea is, Google actually noticed this. They noticed that this is a really common pattern that people have. So internally, they created something called MapReduce, which is their framework for parallelizing that kind of code. OK? There was a paper on this, and they have a patent on this, which was weird. They handle everything like fault tolerance automatically. Now, why is this possible? I'll just tell you, because these are all functions, you can do all the math in parallel, and if something fails, you can just try doing it again. It's not like normal code where if the function was like printing to the screen, printing again might be a bad idea. Because these maps don't do anything other than just transform their inputs, if they fail, you can just do them over again. So that makes it really easy to do the work again. So they handled that automatically, and that created the MapReduce system. People realized it's useful, so they created something called Apache Hadoop. And kind of MapReduce became a general term now. It's not Google specific anymore. It's just the paradigm of programming like this, which is where you have map operations and reduce operations. The actual MapReduce has more stuff than I'm showing here, but this is the basic idea. Okay. So after Hadoop, there was something called Spark that was created in the AMP lab by Matei Zaharia, who's now at Databricks. And it's basically, from what I understand, it's the same thing, but it keeps everything in RAM instead of writing to disk, so it's faster than the previous, than Hadoop. But there's been a lot of work on this, basically. And almost last thing is, if you wanted to have this kind of parallelism, it's actually really easy in Python. You can just import something called pool from multiprocessing. You create a new pool, and then you just say pool.map, and it automatically runs this function across whatever your inputs are in parallel. So you don't need to worry about all the threading stuff that I showed you before, if this is what you're trying to do. But not everything fits into this pattern, so you will need to do that at some point. But this is a higher level threading construct that makes your life simpler. So as I said, not everything fits into that pattern. Some inputs might be generated. You might not know all the inputs in the beginning. Mappers might need to run on multiple inputs instead of one thing. There may need to be a lot of communication between threads, so that wouldn't fit into this pattern. Computation may not even be in a MapReduce layer at all. It might be something else. There's a lot of work currently being done on this. There's a lot of work been done on this, but it's still an open research problem. OK? Phew. OK, just finished. Any questions? Have 1 minute left, so yeah.